So the last bit we want to look at in this chapter is the skill improvements. Of course, along with the increased data, increased spatial resolution and time resolution of the data, in addition to the amount of data, model improvements, model sophistication, computational power has also grown. This is the teraflops of sustained computing power installed at ECMWF over the last several decades, going from 1979 to essentially the present. And you can see the craze providing increasing teraflops, and then you had some Japanese in the middle, Fujitsu, IBM came in, and now we are back to Cray. And you probably have heard of debates about whether the skill at other places like NOAA and CEP have lagged because they haven't been provided similar computing skills as ECMWF. ECMWF has remained kind of a gold standard for skills in forecasting, not just weather and climate, but also extreme events, hurricanes and cyclones and so on. So one always looks to see why they may have an advantage. I have my own ideas, but not so important. The other thing that's happening is to use regional models. So here, interactions between 5 physical parameterization schemes of the weather research and forecasting model. This is courtesy of the Developmental Testbed Center. So the idea of improving models is always complicated. You want to have a frozen version with which you make forecasts, and in the background you want to be able to improve the model and then switch to a new system when it's ready. And many of the improvements are made here in what are called testbed kind of situations, where you have more freedom in a regional configuration with higher resolutions and more local data and so on to look at direct interactions of parameterization. So cloud detrainment with microphysics, cloud effects and radiation, surface albedo and radiations with surface fluxes and planetary boundary layer and so on and so forth. This is also something that is used. These models are also used, of course, for making high resolution forecasts at scales of cities, or for forecasts of floods or urban centers and extreme events and so on and so forth, because they are regional models. They can be run at much higher resolution than the global models, but regional models also means they need boundary conditions, which are typically taken either from the global forecast or done in a hindcast mode, where they may be prescribed from reanalysis products, which are kind of reconstructed past climates and weather, which we haven't talked about much here. Okay. The other thing that's going forward also in the US, for example, is coordination between NOAA, Department of Energy, and NASA in terms of evolving a single model. It's also in addition to the seamless prediction system. So dynamic cores like finite volume are now found to be better, for example, than the finite difference ones from before. There are interoperable physics drivers which allow you to experiment with multiple boundary layer, planetary boundary layer formulations, shallow cumulus, deep cumulus, microphysics, radiation, and so on, as well as other parts of the Earth system in terms of land, hydrology, sea ice wave, aerosols, and so on and so forth, including space weather here. Okay, so seamless prediction can go all the way to space weather as well, right? Why not? So this is how skill improvements are being sought, but also approaches like ensemble predictions are common now. So whereas the other improvements have come from improved resolutions. You can see the different numbers of wave number truncations here and number of levels in the atmosphere, and improvements in data assimilation. Over time period of 2003 to 2017 or so, we are looking at skill relative to ERA interim, which is a reanalysis product, which is a blend of model and data. But their data assimilation is not done for initialization, but is done over historic periods to produce the best dynamically interpolated data. So you have gappy data, and then you blend it with the model and make a dynamic interpolation. So we're looking at mean sea level pressure, 500 hectopascal geopotential, 850 hectopascal temperature, 2 meter temperature, 10 meter winds, total cloud cover, and you can see skill bumps with resolution and data assimilation in some parameters. And obviously forecasters have to constantly worry about improving skills, and some have larger improvements than others. Obviously you can see here, for example, 10 meter wind speed is quite flat, whereas mean sea level pressure and geopotential heights have had skill increment here, and the total cloud cover shows impressive improvements in terms of additions like gravity wave drag and other processes. I think I won't go into the details, but to revisit the ensembling that we talked about, ensemble forecasting is definitely been one method that has allowed for skill improvements, demonstrable skill improvements. Here we are looking at temperature, forecast times, and initial probability distribution, and there is the reality. Before we used to do what are called deterministic forecasts, so one integration of the model, single model integration starting from initial conditions. Here the deviation from reality happens over time because of initialization errors and model errors and so on. So there you can call them initial uncertainties and model approximations. But ensembling takes into account these uncertainties and tries to expand the number of realizations, so that, as we said before, nature gives us one realization, whereas differences in initialization or small differences in initialization would also have probably led Mother Nature to go in a different directions. So the idea of ensembling is at time t, you want to capture the probability distribution of the variable surrounding the reality, so that if you have a good ensembling method and a good model or good multi-model ensembling and so on and so forth, you will span the reality very well around the observed state. Okay. There is a lot of thought that goes into how to generate ensembles, how many models to use, because again you need an optimization of number of ensemble members. You cannot computationally, you cannot have too many members, so how do you optimize the number of ensemble members and how do you generate them? So there is a whole lot of thought that goes into that as well. So compared to the previous 500 hectopascal geopotential height forecast we saw, we are looking here now in the ensemble system, which is compared to some frozen reforecast system as well. So we are looking at 3 days, so time plus 72 hours, 120 hours, 168 hours, so 5 days and 7 days. Obviously the forecast skill goes up with shorter lead time, but the point is that now, for example, something like a 7-day forecast skill is as high as it was for a 3-day skill a few years ago, and so on. So the skill improves, and there is a seasonal dependence of the skill, as we know from before, right? So the signal to noise itself of a variable you are trying to predict is seasonally dependent. Spring, for example, is very noisy in the sense gradients may be flat, variability may be flat, and so on. Okay. Finally, the forecast skill diagram here is looking at skill range in terms of number of days, and scales in terms of finer to larger scales. And obviously there are unresolved processes depending on grid spacing, and depending on the variable there are spaces where there is no skill in prediction. But looking at different quantities like extremes, rainfall, surface fields out to here monthly average sea surface temperature, this gives you again a sense in the ensemble approach where the skills are scale dependent. Okay, so temporal scales and spatial scales for different fields have different skill levels. So here you're going to planetary scales for sea surface temperature at monthly averages for El Nino, and you are much lower here in terms of time scale and spatial scales for upper level fields, for example. Okay, so even though you do ensembling and you enhance skills, the basic skill limitations do exist in terms of what is resolved and what are the spatial scales at which and temporal scales at which you have resolvable signal to noise information. The other approach is to look at, for example, how weather is modulated by climate. For example, here we are talking about El Nino. During an El Nino, for example, the monsoon may have a certain distribution of active and break periods. So active and break periods are not necessarily climate, they are actually in the extended range, but you can go to weather time scale as well and see that ENSO modulates weather. They are called weather regimes. This happens in mid-latitudes as well. So this is an approach, a schematic illustrating traceable and climatic predictability. So here you have traceable predictability, which means that there is the observed event. The forecasted event is slightly displaced in time, but it is still traceable in terms of predictability. Okay, so these are less frequent events, and then you have more frequent events, so you have corresponding observed states. On the shorter weather time scales, individual observed events are predicted here with blue bars with acceptable timing errors with traceable predictability here. Low frequency changes in the frequency or other statistical characteristics of the observed events associated with large scale regimes, however, can be predicted for longer periods. So here your lead times are longer, but that means, remembering this, our spatial scales are also larger. So you may be looking at a blocking pattern instead of a local extreme event, as an example, and so on. Okay, so these are ways in which the same model can be used to enhance skills. There are also ways in which post-processing of forecasts is done, which is very common for weather forecasts. For example, the forecasted variable may not be necessarily what people want, in which case you do what is called post-processing and you derive the forecast of a product for a variable that people want. Could be farmers wanting number of frost days, or temperature for insect infestation, number of degree days, energy requirements, and so on and so forth. So there also value-added products are produced with. There are filtering methods involved here which we didn't discuss in detail, and so on and so forth. So skill enhancement is beyond going beyond the available data assimilation, model resolution, computing power, and so on and so forth to give you skillful, enhanced skilled products or value addition.